Hey, what's up, guys? So welcome to my YouTube channel. Yeah, so basically I already filmed like 6 videos about a category, and there are many other categories. So category is a very large subject in the mathematics, and there are so many different types of category, showing algebraic geometry and algebraic topology, condensed metaphysics, quantum information, and various other subjects, tensor category or something. There are a lot of them. So in this video, I want to introduce a very special group category called the group points. And I think this is the first one that's showing the algebraic geometry, algebraic topology, and corresponding to so-called fundamental group. And I will explain later. But basically, in this video, I want to introduce the basic idea of the group points, and hope you guys subscribe to my channel. Okay, so group point is a very special category, and I will explain in this video. Okay. Yeah. So before I start, let me give you the two different definition of the group points, and one is algebraically, one is category, and we need to connect them. So this is the key point. Okay. So let me just write down a definition. So this is the definition one, which is algebraic. So imagine that you have a set G, okay, and there's a sorry, maybe let me change the color, so make it I can see. So this guy is so this set G has two operations. One is this. This is the partially binary operations. These partially binary are very important. Basically, you just say that you can map G and cross G to G, but partially. So basically, there's so maybe you given any element A and B, these star products do not well defined, right? So this star product only defined in some special case. Okay, and also you have the inverse map. This inverse is well defined. So this is inverse. This inverse is the unary map. So basically from G to G. Okay. Unary map means that you take one group element and spell out another group element. Sorry, it's not group. So this G is called group point if it basically has two operations and satisfy the following conditions. Okay, so the first one condition is that whenever A star B well defined, so I should say if A star B well defined and B star C well defined, then A star B star C equal well defined, and A star B star C has associativity. Okay, so you can see this is very similar, exactly as the same as group. The only difference is that in order for this guy, if A star B exists and B star C exists, then this must exist and they must have the associativity. Okay. Second is that so this unary is always well defined, right? So A inverse is always well defined. All A belongs to G, and also A star. So A inverse star A and A star A inverse always well defined. Okay. Okay, then third fact is that third requirement is that A star B, if A star B well defined. Okay, so if A star B well defined and by okay, so by 1 and 2, I know that I can compute A star B inverse, right? Because by definition, right, your A star B exists and the B star B inverse exists by 2, so this always exists. So the requirement 3 tell you that this guy must equals to what? Equals to A, right? So it's very intuitive. Okay. Okay, and also A inverse star AB needs to be B. Okay. So this is the definition of the group points. Okay, so this is algebraic group point. Okay, so imagine, yeah, and let me just quickly maybe say example. So this is our main example in this video and the only example. Okay, so this example is that so right, imagine that you have a manifold M, which is simply connected. Sorry, not simply connected, connected, and this you can take G to be all paths. Okay, so basically all paths means that a given X and Y you can connect it, and maybe you're very technical, so you can set all paths and up to homotopy. Okay, so basically you can you don't give any points, 2 points, right? But this G is basically all points. Sorry, all F. Sorry, all paths from any. So G is a set of all paths, right? So element in G is just a path. Okay, and what is so what is inverse, right? So if this is your path, then your inverse just map to the reverse path. Okay, so this is the inverse, and what is the composition, right? So you have this star. So star is well defined if the endpoints can be connected, right? So for example, if I start from X and I go to Y, I have a path F, and I get a Z. In this case, that I can create another. I can say that their start will be X goes to Z. Okay, so this star is not well defined for any two of the paths, but with the paths that they can be connected. Also, the sequence, the order is very important, right? Because I cannot do the G and F reverse, right? Because G start from Y to Z and F start from X to Y. Okay, so this is the one example that this is our main example that which you can see that all the paths, right? So all the paths on the connected or even though it's not connected, you can still define this, right? So you can see that all paths has the group point structure. Okay. Up to now we haven't seen what is the relation between a group and group point. Okay. Okay. So now let me give you the second definition, and we will prove that actually they are the same. Okay. So this is the categorical. So categorical definition for a group point. Okay. So the definition is a small category. So small category, as I mentioned, that basically is the object. Say this is C, the object C, and the home of any two objects are sets. Okay, so a small category with all morphism is isomorphism. Okay, so this means what? Remember what is category, right? So given any two object X and Y, you can define F, and by this constraint, there is always a G, such that G circle F and F circle G is identity. Okay, so G circle F should be identity on X, and F circle G should be identity on Y. Okay, so this is the definition. Very simple, right? Okay, and let me just spell it. So let me just write down. So this is equivalent that you can define a set. So let's say G0 is a set. So this is a set of all objects. So of all objects. Okay, so since it's small, right? So G0 it can be a set. And for any X and Y belongs to G0, you can define a home set, right? So you can define a GXY, which I define to be, maybe I use this G, okay, as a G as a group point. So GXY is a home, right? Home map. So basically it's all the morphism from X to Y, and maybe empty, okay? Such that what? Such that which is category, right? So basically you should have the identity map on X. So there's always one special map identity special morphism in GXX belongs to GXX. And also there's a composition that you can do, right? So there's a composition such that if you have the GYZ, cross gxz, so x and y. So this means that x mapped to y and y mapped to z, right? So map to g xz. So this is g, this is f. You can compute gf. Okay, and also there's an inverse. So this is 1, 2, and 3. There's an inverse. Okay, so this inverse is just in a category. Sorry, not in the usual category, right? But in our group point, because in group point that every category, every morphism has its inverse, right? So I can define inverse, right? So then that means what? That means that somebody give you f in the g, x, and y. That you can spell out the inverse, f inverse, g, y, x. Okay, and there such that there is a relation such that f identity x equals f, and the f let's say identity y equals f. So let's say f belongs to g, x, and y. And also obviously that you have this, right? This is the composite. This is the definition of a category, and then you have the inverse. Okay, so this is the category called group point. Okay, so now let's prove that actually let's explain why this group point category is the same as algebraic category. Algebraic group point. Okay, so theorem, which is our main theorem, basically the group point of the definition 1 and the definition 2 are equivalent. Okay, so what if you understand this, then you can start to in algebraic topology, you can start to pull all the group point. You can pull the fundamental group into the group point. Okay, and once you have this, then you can understand many deep mathematical structure if you know about group point. Okay, so let's explain. So since it's just equivalent, so I just explain it. Okay, so let's do. So what? Okay, so let's start from category 1, category to algebraic. So imagine that somebody give you a category G, right? And you want to construct this algebraic category. So sorry, algebraic group point. Then you just take G to be let's say GXY. So this is band notation, but this left hand side is algebraically, and then for right hand side category, so this is algebraic group point, and then for category just take all the XY belongs to the object, right? G. Let's say G tilde. So G tilde will be group point, will be algebraic group point. If you take G to be a group point category, okay. And this proof is trivial, right? Because of the composition. Oh, by the way, this is disjoint union, right? So the composition just the category, I should say the star, the usual star, right? The usual star in the algebraic group point defined to be the composition of the original category, right? Because any two you may not do the composition, right? You may not do the composition if x and y do not compare with itself, right? So it must start from let's say x to y and y to z. Okay. And also inverse is just what? It's just the isomorphism, right? So you just define the isomorphism. And so given any f belongs to this, then you just define f inverse. So f inverse is already defined in a categorical group point. So in algebraic group point, you just use this unary map as a f inverse. Okay, so this is the trivial. And moreover, you can easily prove this, right? This is just identity, and yeah. So this is also trivial by isomorphism. So from category 1 to algebraic 1, this is almost trivial. So the only probably the difficult one is to start from algebraic. So we should start from algebraic group point. and try to go to the category called group point. Okay, so this might be a little bit difficult, right? Because I start from G and I need to go to the categorical one, right? So I need to find a set, define a home set, and find a composition, and whatever, right? I need to prove everything. So this direction will be a little bit difficult. Okay, so somebody give you algebraic group point. I need to construct a object, right? So I can define G0 by G modulo something. And this modulo defined to be, remember that in the algebraic group point, I have a star and the inverse. I can define a G0 to be G quotient something. Okay, so in this case that we may have very good intuition, right? Because in the G, I get some pass, right? In the fundamental, in the manifold case. So I should go it back, right? And then get the points X, right? So I can define G0 to be G quotient this. So basically the quotient means that if A star A the same as B star B, B inverse star B. So basically I define G0 to be the equivalent class. What is the equivalent class? Such that A inverse star A equals to B inverse star B for A, B belongs to G. So basically, if I have all the paths and I go back to the path, then I will locate the points. Okay, so once I have this G0, then all the sets, all these all sets G0, imaginary should be all the points, right? So G0 should be the points, should be all the points on the manifold. So this is the one imagination that you can get, right? But basically, algebraically, you can just define this. Okay, and yeah. So how about morphism? Morphism just using the composition to define morphism. Okay, but before that, I should define a home set, right? So now let's do this. So I can define a G of xy. By the way, I define I write element in G0 as identity. Okay, so this is very weird. Okay, so I write identity X as the element of G0. So imagine that I just sit in X and I don't do anything, and so X belongs to G. So any equivalent class X belongs to G0, I write it as 1X. Okay, so G of xy define. So given any element F, so G of xy defined to be any F belongs to G, such that 1X star F star 1Y well defined. Okay, so given any F belongs to G, remember that the imagination is that this G contains all paths. So I define F, which that the composition with 1X and 1Y means that the imagination start from X, Y, right? Can I connect them? Well defined. Okay. Okay. So this is a definition. Okay, so very easy exercise to show that this is basically the category which you have. Okay, so now let's quickly. So now we have this G0, right? And then we have identity by definition, because identity by definition your the ID your 1X, right, belongs to originally belongs to this, right? Because you have a identity map. And so the only non-trivial part is that you need to check this composition. So let's quickly check it. Yeah, this composition is a little bit tricky. So let me just quickly check this one. Okay, so let's see. Right, so let's say F belongs to this GXY. So remember, F belongs to GXY means that 1X, F, 1Y. Okay, so I neglect this star because it's troublesome, right? It's well defined. And then let's say your G. belongs to G, Y, Z. So imagine that Y go to Z, where it means that 1Y, G, 1Y, 1Z is well defined. Now I can compute F star G, right? So this star is just this star, right? So in this star is in algebraic one. Okay. And I define F star G in algebraic one defined to be, I define the G composition with F defined to be F star G. Okay, so let's compute this. So you get the 1x F 1y and 1y G 1z. Okay. And right, so what? Right, so you get 1x fg 1z. Okay. Oh, by the way, I should say this, right? And remember that this 1x in this case, your 1x is defined to be a star a inverse star a, right? So which means that this guy do it twice, right? You can do this. Well, composition twice will still be this, right? By our formula, right? So this guy will still be it, right? So you can easily check this. So will still be let's go to the first definition, right? So you get this, right? So okay, so you still get this. Okay. So this is why you can cancel these two, and this is the composition. Okay, so you can see that by the existence, this fg can be defined as this fg can be defined as from fx to y to z. So this gf basically belongs to g what g sorry, I'm stupid. So x to y, y to z, right? So I can define it to g to be xz. Okay. Okay, so this is the you can use. So we've already checked for the composition. So and this is just the definition. Yeah. So this is just the results. Okay, so proof. And then you can define. So usually people write G1 using this. So usually this is a group point. And notation means this arrow means some two arrow because you should label two of them, right? Because you given any 2 points of G0, then you can construct a home set. Okay, so this is why there are 2 arrows. And usually this X is called source, this Y is called target. Whew. Why math is so difficult? Okay, so from here, let me just quickly make 2 definition. So given a group component, okay, so up to now, I define a group point using a categorical one, right? So I have a group point such that I have a small category such that all morphism are isomorphism. Group point, and I can define as gxx, right? So your exercise, which is a very trivial, gxx is a group. Okay, so this is let me just quickly mention. So this is trivial, right? Because by definition, your gxx in a categorical one is basically every morphism in this has its inverse, right? So basically you have inverse, and the composition and identity are already built in gxx. So that's it. So gxx group. Okay, and this is called the vertex group. Okay. So you can start from group point and get group, right? But just put 1 point. Okay, and also one can define another object called the orbit of a group point G at point X. So let's say you get some point x belongs to G. So this is a band notation, right? But when I write x belongs to G, I mean that x is the object of G. So now G is a group point, okay? So orbit of Gx at point of x belongs to G is that, so imagine that I should say the points, I should say informally, the points can be connected from x. Okay, or basically mathematically, I should say y belongs to G such that Gxy is non-empty. Okay, so basically this just means that suppose you have two islands, two different topological space, and y and x, and this is z, right? So z and x, there is a path that you can start from x to z, right? So z will belongs to the orbit of x, but y will not be the orbit of x. Okay, and mathematically you can say their fundamental group are the same. Okay, but the problem is that these if you, there may be different paths from z to x, so or x to z, right? So actually you cannot, there's no canonical way in general. Okay, yeah, so this is the group point, and yeah, and there's a very easy result that gxx and isomorphic to gyy if y belongs to orbit of x. Okay, the proof basically given any, let's say let's say you pick any G and belongs to this, and there's a maybe a path, right, which connecting x to y, or basically the non-empty element in the G x y, let's say F, that you can try to compute, you can try to map this Gy. Okay, you can try to get your Gyy. Okay. Yeah, so you can check that this map to be Fg, F inverse, okay, will be the isomorphism of these two. So basically this turn out in the fundamental group language is basically 2 points. If they are in the same connected component, they have the same fundamental group. Okay, so now we already introduced group point. So let's working out the example that the only the main example that in the algebraic geometry, a topology. So you can, in somebody give you a topological space, you can define and given a point x zeros, you can usually you can define, so you always can define a so-called fundamental group. So it doesn't need to be manifold, right? X can be any topological space. So fundamental group, and the definition basically is all a continuous map from F. Let's say you're given the unit interval 0, 1 map to X, such that f of 0 and f of 1 is basically x0. Okay, so this is all the paths from x to x0, x0 to x0. Right? So imagine that you have space M and then x0, and this map. Maybe you go from this space and go it. This is you already go this and you go this. Okay, but up to quotient homotopic path. So homotopic. This is not important because I'm not talking about detail. Okay. I will talking about the fundamental group in the future. Okay, so but basically, you can check this is the non-trivial case, non-trivial results, but your pi1 of x0 is a group. Okay, and usually it's a non-abelian group. Okay, so for example, the famous results maybe the pi1 of the circle will be z. Okay, and this is the same as the homology of the circle. And by the way, this is not accident. Okay. Basically, you can prove that the first homology is the abelianization of the fundamental group. Okay. And but there can be non-abelian. For example, if you compute phi1 of figure 8, such as 8, and you can check that the least path, let's say this path is A, this path is B, you can check that if you go A and go B and go A, they are different. So this guy is a Z with the so-called free products. Okay. I just a very quick example, pi1 of pi1. Okay. So imagine, so now given a manifold M, let's say this is connected, then x0 and y0, x0 and y0 can be connected by any path, right? So this tells me that the pi1 of x0 is isomorphic to pi1 of xy0, or basically pi1 of any base point, right? So this is called base point. So basically in each space, in each point, I have the same group, right? So this is our algebraic, this is our group point. So you can make, so now I can make, and then notice that I can make this pi1, very bad notation, this pi1 of x, pi1 of x defined to be the fundamental group point, okay? So the fundamental group point is a group point such that that's given a definition, right? So object. So what is the object? Give me 2 points. Okay, so give me 2 points. I can sorry, so object is a point on M. I'm stupid. So x belongs to M. And the morphism. So somebody give me x and y. I can just connect it a path. I can just find all paths connected to x and y. Okay. And the composition, just a composition. Okay. So you easily can see that this guy is a group point because each morphism, each morphism, each loop, if I can go from x to y, x0 to y0, I can just go, I can just turn it back. I can just turn it around. So easy to see that this pi1x is actually a group point. And the difference is that now if you take the previous my definition, I call it what? I think I call it the vertex group. If you take the fundamental group point and take the vertex group, then you will get the x0 and you will get the fundamental group. Okay, so this is very interesting that in general, in a unified framework, that you usually think that fundamental group is the elementary one, but actually you can combine everything in terms of the thing called fundamental group point. And sometimes that if you think about the fundamental group, not just a group, but contains all different M into the fundamental group points, then you can get something very interesting. Okay, so this is, let me just finally give the remark. Okay, so if you learn about the Van Cappen theorem, hopefully I didn't, I think I misspelled this. Okay, so this theorem should be called the Van Cappen. Okay, yeah, this is called Van Cappen theorem. Okay, so if you learn about if you know about the Van Cappen theorem, then you know that this is a tool showing the LA Hatcher to compute the fundamental group, right? So basically, the idea is that if somebody gives you like if you can separate this x into the U1, maybe union U2, and both are paths connected, and you can get your pi1 of x by getting compute pi1 U1 and pi1 U2. Okay, but actually the Van Cappen theorem has much as a beautiful results if you write them into write fundamental group into the fundamental group point. Okay, so this is, let me just quickly say this. So actually, if you take, you can define a pi1 of xa, by the way, and you can make this guy in terms of so this is a fundamental group, right? But with a, so you can make it so-called subgroup points of the fundamental group, and you can define this. You can, so the Van Cappen theorem has this form. Okay, touch it like this. So you can separate x into x1, x2, and x0. I think it's their intersection. So x0 is x1 union x2, and then let's say x is you can separate x into the x1 union x2 with its interior. Okay, And this guy, this is what we want to compute. Actually, this is in a group coin in the category language. This is called push out. Okay, so actually the Van Capen's theorem, if you spell it using the speaking it using the group point language, then you are just saying some push out of the original category. Okay, so this is very interesting example that I think the fundamental group is maybe the first example, the most intuitive example to ask, to give you a feeling about what is the group point. And yeah, hope you guys like this video. And in the future, maybe I will talk about a monado category, a ribbon category. I think they're also interesting. And also, I want to talk about the representation category, which is contains very interesting uh, aspect. Okay, so yeah, so this is my video about group point, and I use fundamental group as my example. Okay, so see you guys next videos.